Welcome everyone to geometry. We want to continue taking a look at section 5 on area. And in this video, we want to look at the scale factor and the area factor. So we say that figures that have the same size and shape are congruent, right? Same size, same shape, congruent. They're going to have the same area. We looked at that earlier. But if two figures have the same shape but not the same size, are called similar. So all squares are similar because I can just blow one up or shrink it to be another one. Triangles, it's a different story, right? I can change how a triangle is shaped. So I could have one that looks more like this and another one that looks like this. And no matter how much blowing up or shrinking that I do to this guy, I'm never going to have it be that guy. So all squares are similar. And for example, these two triangles down here are also similar. So notice here that I can get this side length by doubling this side length, and I can get this side length by doubling this one, and I can get this one by doubling that one. So we've doubled all of the side lengths. So we can take, when we have two similar shapes, every one has a number, right? This one is 2. I multiply sides by 2. Every pair of similar geometric figures has such a number, and this number is called the scaling factor or scale factor. In some texts, you might see it called the constant of proportionality. We'll call it the scale factor, or SF for short. So in these two triangles, the scale factor is 2 because I multiply by 2 to get over here. So the scale factor is 2. Now, if I wanted to move from the triangle on the left to the triangle on the right, I may have said the scale factor was 1/2. So it does depend on which way you're traveling here in your scaling. So you want to be careful about that. So any pair of similar figures also have an area factor. So scale factor is how the side lengths are changed, and the area factor discusses how the area changes. What are we multiplying by to change the area? So what is the area factor in the triangles above? Well, if we call this triangle A and we call this triangle B, the area of A is equal to, now you might say to yourself, well, all right, so now we need to find ourselves a base, call it this guy, then we need to find the altitude, but don't overcomplicate things, right? Any side can be the base, not necessarily the one on bottom. So if we call this the base, then the opposite vertex would be this guy, and the altitude would actually be this side because that side is already perpendicular. So the height would be 8. So with a base of 6, we would have a height of 8. Or you could choose this to be the base, and then 6 would be the height. So, but either way, base times height is 6 times 8. So we've got 1/2 of 6 times 8. 6 times 8 is 48. 48 divided by 2 is 24. The area of the triangle on the right is 1/2 base times height. So if you do the same thing, base times height, 3 times 4 is 12, and 1/2 of that would be 6. So the area factor, which we can abbreviate with AF, again, moving from the smaller triangle to the larger, would be multiplied by 4. Excellent. Area multiplied by 4, you get the second area. So let's use a measuring device to estimate the scale factor of these two squares. Now, I don't have any measuring devices handy, so what we could do is we could take this square, copy it, and move it over. Unfortunately, I don't think that I can copy and paste. No. So, oh, but maybe this will tell me. Oh, no, it doesn't. All right. I was hoping maybe like when we turned, it told us how many degrees. It might tell us how many, how much we're scaling it. So not the case. So if I copy it and I copy it, I can keep moving these over to give me an idea of how large it is. So this will take me a moment, but that's okay. If you're watching this on the Zoom link, you would be able to fast forward. If someday this ends up on YouTube, you won't be able to fast forward. So we're almost there. If I were to just do a couple more here, like this, and actually maybe do one more, carefully placed here. So you can fill in, there'd be a box here, 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 right? I think we can see that. Excellent. So this gives us an ability to approximate our scaling factor and our area factor. So it looks like there's about 1, 2, 3.5 squares long, 1, 2, 3.5 squares long. It's not perfect, but that's about right. So that would give us a scale factor of 3.5 because it took me 3.5 squares to get across. Now the area factor, if it took me 3.5 and 3.5, then I'm going to have 9 squares here. 1/2, 1/2, 1/2, so that's 1.5. 1/2, 1/2, 1/2, that's 1.5. So 1.5 plus 1.5 is 3. Plus 9 is 12. And I've got a quarter here. 12.25. Excellent. If you'll look carefully, I believe this is actually equal to 3.5 squared. Interesting. All right, so let's do the same thing with the triangles. This looks much better because with these dots, it'll be easy to calculate side lengths. So we can do this as a calculation instead of an approximation. So let's compare two of the same side, or the corresponding sides. This one has length 3, this one has length 2. If we considered those our bases, then this would be the height of, let's call it triangle A, which is 1, 2, 3, 4, 5, 6. And this would be the altitude, I guess, not the height, but the altitude of triangle B, giving it a height of 4. So for the triangles, the scaling factor, if I'm going from 2 to 3, I'd have to divide by 2 and multiply by 3. Excellent. Now to get the area factor, I'd have to calculate the areas of both of them. So the area of triangle A, this is equal to, all right, so 3 times 6 is 18, divided by 2 is 9. The area of triangle B, 2 times 4 is 8. 8 divided by 2 is 4. So the area factor would be equal to, let's see here, to go from 4 to 9, I'd have to divide by 4 and multiply by 9. And what do you notice about this? Well, shoot, that's just 3/2 squared. So with that, between our last two examples, we should be able to see, or at least have a good guess at, what the relationship between scale factor and area factor is. So area factor turns out to be the scale factor squared. Excellent. So let's take a look at a few examples of applying this concept. A certain youth soccer field is 60 yards long, while a similarly shaped adult soccer field is 100 yards long. I should say similar shaped, right? Not similarly, similar. The two soccer fields, the shapes of them are similar. So the larger one, the adult one, is 100 yards long. If it requires 55 pounds of fertilizer to cover the entire youth field, how many pounds are required to fertilize the adult field? Well, this seems a little bit weird because we're talking about fertilizer. We're not talking about areas. But the reality is if we're putting the same thickness of fertilizer down, then the volume could simply be measured by the area that we're covering. So 55 pounds of fertilizer we can think of as the area. So it's an alternative measurement, but measures the same thing. So we need to identify the area factor and multiply by the area factor to go from the youth field to the adult field. We can do that by first identifying the scaling factor. And the scaling factor would be given by the adult soccer field is 100 yards long and the youth is 60 yards long. So to go from the youth to the adult, this is the scaling factor. We could simplify this to 5/3. That tells us that the area factor is equal to 5/3 squared, or 25/9. So that gives us our area factor. So we take our 55 pounds of fertilizer, which represents the area, and we multiply by 25/9 to give us 153. So 153 pounds of fertilizer are required. Excellent. So let's consider another example. A 2-acre field is 100 yards wide. How wide is a similar shaped 10-acre field? Now, acre is definitely a measurement of area. That's explicit. Might not be a measurement we're familiar with, but that's fine. We don't have to understand what an acre is. We just need to know that it's describing area. So in order to go from the 2-acre field to the 10-acre field, we want to find the scaling factor. So, actually, not the scaling factor. In this case, we're working with the area factor. We want to find out what the scaling factor is because we want to find out lengths, or widths rather. So we know the area factor to go from the 2-acre field to the 10-acre field. Again, we'd have to divide by 2, multiply by 10. So that's 5, right? We multiply by 5 to go from the 2-acre to the 10-acre. That gives us that the scaling factor, right? The scaling factor squared is the area factor. So the scaling factor has to be the square root of 5. So the width of the field is, right, 100 times the square root of 5, which is about 223.6 yards. Excellent. So we were able to find the width of the larger field. It's 5 times larger, but the scaling factor is only square root of 5, or 2.236. All right, so let's suppose we have similar triangles A and B. Let's see. Here's triangle A. Here's triangle B. Triangle A is larger. It's 44% larger than triangle B. By what percentage are the side lengths of triangle A greater than the lengths of triangle B? Well, that's interesting. Percentages. So from this, if we get the area is 44% larger, that actually tells us that the area factor, right, it's not 44% because it's 44% larger. There's 44% more than the 100%. So there's 144% to go from triangle B to triangle A, okay, because this is 44% larger. That tells us that the scaling factor is the square root of 1.44, which is 1.2. So we have to multiply the side lengths by 1.2. That is, the side lengths are 20% larger. The side lengths of A are 20% greater than the B sides. Which is just kind of a fun and interesting statement. Anyway, because anybody familiar with records knows that the better songs are on side A and the not as good songs are on side B. So listening to the B sides is referring to listening to side B on records. B sides. All right, anyway, so one more example and then we'll be done. If we decrease the side lengths of a parallelogram, if we decrease the side lengths by 15%, by what percentage is the area decreased? Well, if we're decreasing the sides, right, we're having some scaling factor. And if it's 15% less than it was, that means that it is 85% of what it was. So if we reduce it by 15%, that means it is 85% of what it was. So 0.85 is the scaling factor. Awesome, that's not so bad. And that tells us that the area factor is equal to 0.85 squared, which is 0.7225. All right, so that tells us that the area has been reduced to 72% of what it was. So it has been reduced by, let's see, that'd be 27.75%. Area is reduced by 27.75%. Excellent. So that's the last example for this section. So we are all set with this section. We'll move on to section 6 shortly. Videos for that will be posted hopefully in the next couple of days. Have a wonderful day. I'll see you guys soon.